So, good morning to everyone, and this is the session related to design for test, which is one of the working core domains of semiconductor. Today, we are going to discuss a little brief of what is DFT and what is semiconductor in the first place. And many of you are from uh, college passed outs, and those are working parallelly already in other domains. Want to change the domain. For everybody, those who want to enter into semiconductor, this is a good start and uh, the first stepping stone where you start learning uh, the technical concept which is needed to enter into semiconductor. So myself, Ganesh Kumar, I have done my masters in VLS system design, and I'm the co-founder and CTO of Success Bridge. I have 10 plus years of experience in VLS industry. I'm a DFT architect, and I have very good experience in designing SOCs for many applications in terms of medical and military grade, as well as automobile, mobile, um, and network and computer computer chipsets. Okay, and I have started my uh, work career in 2012. Okay, and I have done my masters and parallel is working. I have vast experience with all the product based and service based companies that I have worked in Hyderabad, Bangalore, and currently I am located in Malaysia, working for Intel. Okay, so I'm going to guide you through the DFT and semiconductor, the concepts, and any insights and guidance needed for you guys to get into the industry. Okay, we'll discuss everything, and I'll be going forward. I'll be the uh, trainer for those who have registered for the course. So today's agenda will be introduction to chip designing and latest trends in semiconductors and some of the challenges and geopolitical issues affecting semiconductor industry and career growth and future scope in semiconductors, and we'll have some discussions. Okay, so first of all, the semiconductor is for everybody. Those who have done BSc, BE, ME, BTech, anybody can enter into this semiconductor, but it will be more meaningful for those who have done their BTech or BE or BSc electronics. Uh, so more into electronics and electrical or instrumentation. It adds more value into that. So as long as you're learning the course, you are good to go, because semiconductor is not something that you learn. I mean, you are directly taken from the colleges, and then they train you, and then they give you the projects. It doesn't happen in semiconductor. You have to be a trained engineer in any of the working core domains, because none of this is taught in academics. Unlike C, C++, Java, networking, all these are taught for CSC, IT domains in engineering or their academics. But this particular real-time domains in semiconductor, like we'll discuss this going forward. So these working domains in semiconductor are not taught in academics. Okay, and the good thing is uh, the basics are same. The same digital logic design basics. All you need is to understand what are logic gates, how many logic gates are there, okay, and what are the truth tables. How do you write a Verilog coding? and understanding the Verilog coding. So these are the simple fundamentals of entering into semiconductor. Unlike software, we do not have to learn every upcoming software coding or software methodology or technology. Uh, we have a fixed things like our entire chip is based on the same fundamentals of NAND gate, AND gate, OR gate, or whatever the combination logic gates that you have learned in your academics. Okay, so our fundamentals are same. That's a good thing. Okay, only backdrop is that you are not trained again in the companies. You have to get trained here by any of the training institutions. Okay, and then get placed. So when you go for a interview in any company as a fresher, they expect you are a trained fresher. Okay. Okay. So coming to this picture that you're seeing, this is the cycle of the chain of semiconductor. Now, as you guys see, this is a design IP. Okay. So your IPs, intellectual properties like individual uh, IPs, ARM processor or ARM related uh, IPs are designed by ARM, individual IP vendors. So like ARM, there are many individual IP vendors. They develop their own individual IPs and sell them. Okay, so they have nothing to do with other IPs in the complete chipset, because if you are taking a mobile chipset or a laptop chipset, there are multiple IPs. IPs in the sense the IC, each individual IC, or if you're talking about a hard IP, it's each individual small IC or large IC. It's an individual IC. Okay, we call it as an IP because it is an intellectual property designed and developed by uh, the companies, the individual companies. Okay, so design IPs are coming from individual vendors, third party vendors who are specialized in designing that particular IP. Electronic design automation is something where we use the tools, EDA tools like Cadence, Synopsys, and Siemens Mentor Graphics. Okay, Siemens and Mentor Graphics are same. Mentor is owned by Siemens now. Okay, so these are the end products. Okay, in the cameras, applied materials, ASML products. Okay, all these are the end products, and these are the raw materials that we use for designing the chip. Okay, and these are the foundries. Only few we have here are the few. Okay, TSMC, Global Foundries, UMC. These are the foundries where the silicon wafers are manufactured, and on silicon wafers, chipsets are uh, designed, fabricated. And this is the testing and packaging assembling uh, companies, which is Advantest and Teradyne are the most popular. Each and every company uses this, okay, for testing. So DFT comes into picture. uh, I mean, it plays a major role in the entire chip designing, because before going to before going to the foundry, and after the chip is get manufactured and going to the customer, it has to be tested. So testing happens both pre and post manufacturing. Okay, so as a DFT engineer, we fall under uh, pre as a pre silicon first testing, pre silicon testing, and we provide test patterns proving that this design is fault free. So we'll discuss going forward. And these are fabless designs. So there is a differentiation between foundries and fabless designs. All of you might have heard about Broadcom, Nvidia, Xilinx, AMD, Qualcomm, MediaTek, Marvell. These never manufacture. These are fabless designs. Okay. These designs are manufactured by somebody else, like this foundries. Okay, so this is something like, how do we say in a uh, practical way? In reality, uh, if we can take up any example, uh, mm, so water supply system. So the water supply system, water is very much common, where each individual water packaging suppliers use the water and package them individually. But water is it's a available source from the earth. So we everybody has the access, but those who package and sell it, they make money. Similarly, here TSMC Global Foundries are the foundries, so anybody can come. Like Qualcomm becomes the client to TSMC. You can come and give me a chipset and get it manufactured. You want 10,000 pieces or 1 lakh pieces, 10 lakh pieces, uh, pieces in the sense the chips. I'll give you at this price. So all the fabless designs will not have fabrication units. Okay, that's what it is, fabless. So there are many fabless. You can see fabless are more, fabs are less in the world. Okay. So coming to these Texas Instruments, Samsung, Micron, Intel, onsemi. Okay. Uh, all of these, majority of these have their own fabs. Intel has their own fab, Micron has, Samsung has, TA has. Okay, all of these has their own fabs similar to foundries, but these are individual. These don't act as a foundries unless until required. Let's say Samsung also takes clients, provide as a foundry service. That means Qualcomm can come to Samsung and say, it's urgent, I need my ICs gets manufactured under your foundry. That is still accepted. So this is how it is, the overview. So there are differentiations here. We already discussed. This is just a representation of what are foundries, what are the power semiconductor companies that are dependent, and what are the clients, what are the end product and customers in automation and uh, electrical appliances, electronic appliances. Okay. So coming to ISIS, we have these three major differentiations. I have made it four for your understanding. Again, CPU and GPU will come and sit in ASIC as well. Okay. So CPU is a individual processing unit. Okay. So you categorize it as a CPU. So majority of your Intel processors or AMD processors in your mobile chipsets or laptops, you see processor is separately uh, placed. It's a individual component. Okay, so GP is also an individual component, and FPG ASICs these are boards. Okay, an ASIC is a combination of multiple IPs. So ASIC can become a microcontroller, microprocessor with multiple uh, peripherals and components. Okay, so end of the day, you will be designing an ASIC, application specific integrated circuit itself, which will have a SoC. Okay, so in an SoC, you will have all the CPU, GPUs, all these things. So major differentiation would come where FPGA is a separate thing. CPU, GPU, ASICs are all same. Okay, so these differentiations you might have learned from academics of engineering or from your Bachelor of Science, but still we will be learning this part of our course. This is just basics of understanding. So life cycle of IC packaging. Uh, these ICs have packaging uh, technologies where we package these ICs using these technologies in terms of you want to package them in a 3D IC structure or a 2.5D IC structure, okay, or a single IP structure. So it all depends on end product, how it is going to function, and what is the usage, where it is going to be used. So based on that, starting from 1980s to now, we have got upgraded to a much more advanced packaging technologies. So where we are now working on a 3D IC fibers and move on to heterogeneous integration, where that is called multi die chipsets. So this is one of the Thunderberry 5, which is a replica of your Raspberry Pi. Okay, so it has a Qualcomm Snapdragon processor, which is this particular Thunderberry 5 is used in engineering projects. People use Students use this in engineering projects. So uh, here, as a DFT engineer, you care about digital logic, okay, and through digital logic you program everything for your SoC design, and this SoC design controls all the peripherals, IOs, everything that are all the sensors, analog design, everything that is connected to this SoC. Okay, so going into deep, I'm taking one Samsung here, Samsung chipset. This is your Snapdragon processor, and this is your audio codec, RF Fusion, Skyworks, flash storage, memory of this particular Samsung. So all are individual components on a chipset. Okay, majority space occupied by your battery itself. Okay, so this is your mobile phone, and this mobile phone, you see what is the size of these individual components and the placement here. And this is your, on the left side, you see this is a block diagram representation of your Snapdragon processor. So this particular Snapdragon chipset, this particular chipset is having inbuilt GPU, okay, sensing hub, process security, cryo CPU, fast connect, and 5G modem system with memory. Okay, so you work on as a semiconductor engineer for a digital design engineers. They work only on the digital part, which can be written through Verilog coding. Okay, only digital part. So you verify digital part and you add testing logic to that and provide test vectors to the tester. That is the role of a DFT engineer. So this is partition further while working. So uh, GPU will have multiple. It's like a subsystem. It's a subsystem. This is subsystem. Memory subsystem. So internally, memories are divided into multiple sub modules and sub individual IPs. So if there are 10 members, 10 employees in the team, so each employee gets some few blocks, okay, few blocks, and they perform the DFT for that particular block. And this structure is same goes with the verification engineer or a physical design engineer. So the ownership of real-time engineer is something that you own certain particular block, let's say module memory, one or two. Okay, whatever that particular module definition or that logic is there of that particular module, you need to add test logic to that using the EDA tools, and you need to test it and validate it, and you need to uh, write out the patterns, generate the test patterns using the tool itself again. So in a semiconductor, majority of the newcomers have no idea what exactly happens in semiconductor is. 80% of the work is done by the tool. Okay, 80% work is done by the tool, but we don't trust the tool. That is why engineers are needed. 80% of the work is done by the tool because we have encoded the tools with proper engine needed to support all these functionalities. Okay, so tools are provided. Tools, the EDA vendors like Mentor Graphics or Cadence or Synopsys, they contribute a lot. They upgrade every 6 months. They provide new. They do R&D with all the major MNCs like AMD, Nvidia, Synopsys, Intel, all the manufacturing companies. While they are using their EDA tool, they find bugs. They find they feel like new innovation is needed here. We tell them, they add this into the next release in next 6 months, or they fix it in next 1 or 2 months if it is very critically needed for the project. So EDA vendors are totally dependent on the chip manufacturers. Okay, and 20% of that remaining is done by the engineer. You have to handle these tools, EDA tools, and you need to understand the document of these tools and take the script from the tools and control the tool to perform setting up our needed operations. How to test, how to read the libraries, how to read the design, how to write out the design. All of these are part of DFT engineers work. Okay, this is some Apple chipset. This is I have taken this up just to tell you guys that on a single chipset you will have multiple vendors sitting on. Okay, if you see, Apple is so famous for its individuality and uniqueness, but if you see, Apple has Micron memory, SDRAM memory, and the generator buck regulator is from synchronous regulator is from on semiconductor. Taptic engine driver. Okay, the sensors are controllers are from analog devices. Similarly, NXP semiconductors, display ports, Texas Instruments for USB 2.0. So not necessarily be that all the ICs, the Apple has everything manufactured in its own in-house. Now it is going to, because it is not going to trust other third parties, but it doesn't happen with everybody. Not entire chipset, the application that you want to end application will not be designed by a single in-house company. Multiple companies work together. Okay, so it's a contribution of everybody. So end of the day, the thing that plays majorly in the semiconductor is which technology node you're using. So if you are using 2 nanometer, majority of the time, for the timing sake, to meet the static timing analysis in the end of the day, you maintain for all entire chipset, you maintain that 2 nanometer technology only. That means each component here in the chipset will have the same 2 nanometer technology. So this particular on semiconductor should be ready with the 2 nanometer IC of this is regulator. Similarly to the mic NXP, Texas. So all they are individual IP vendors. So that is the reason we say IP vendor. They are expertise in designing their own individual components and they're ready to sell it. So this Apple buys it and place it in its uh, chipset. Okay. So I'll not go much depth into things. We'll have more discussion. Okay. So this is the entire semiconductor flow where we start coming with a specification of what we want to design. We want to design an automobile SoC design or a mobile phone SoC, computer SoC, uh, or what kind of SoC you want. That we will decide first. And let's say a customer coming to you like OnePlus or uh, MI, Xiaomi, Samsung. Samsung is its own fab, so it doesn't come Note. Okay, so now OnePlus. Let's take OnePlus, and OnePlus is coming to some Intel, who is a chip designing company. It provides services for chip designing. That means it has engineers to support for all these entire end-to-end chip designing, and it can deliver the product. So if you want it fabricated in Intel also, it can do now in the current scenario, because Intel has moved to these foundry services recently. So if not, it can process up to this layout post processing, and deliver it to the customer, and customer can take this and manufacture it to anywhere, any foundry it wishes. Okay, but end of the day, again, we are using some technology node, and you use that technology node libraries coming from that foundry. So if I say that, if you're coming to me, I am Intel and the customer is OnePlus says that I need my mobile phone to be manufactured, designed at you, and end of the day I will get it gets manufactured in the TSMC. So he has to get the TSMC libraries first. So that 5 nanometer or a 2 nanometer libraries has to be purchased, and he has to tie up with the TSMC stating that it will be designed in Intel, and again I'll come back to you for a fabrication or manufacturing. Okay, so this is how. Now architectural design, this is one role. System specification, architectural design, this is one hierarchical first stage. Okay, so architectural design engineers are seniors, those who discuss with the client stating that this is okay, you want this, okay, this can be done, this cannot be done, that will be discussed. Next is the functional design and logic design, or functional verification, you can say, RTL design and functional verification. So RTL design is one designation, functional verification is one designation in real time. Both are two different works. RTL design writes the Verilog code, and functional verification engineer has to verify it and simulate it and state that, okay, I have given this stimuli and I got this response, it is valid. Purely to validate the syntax and code correction, functionality wise testing. Next, RTL synthesis and physical design. Okay, I'm comparing both of this. Okay, so RTL synthesis is something that RTL is written in a Verilog code, and it has to be converted to gate level. That is called synthesis. Okay, when you do synthesis, it gets converted into a proper gate level representation. If you are using AND gate, it will be like a proper AND. This is your AND library. Okay, this is your AND input ports, output ports. Okay, so likewise. So that is done by either RTL synthesis team if you have for that particular company. If not, physical design team will do that for you, because they cannot work on RTL. Physical design has to convert RTL into gate level. Then only they can start working in their set of operations. Now DFT plays a middle role where you take up this RTL synthesizer netlist, okay, and you start working on that. You insert additional logic, that is DFT logic, and finally you validate it and you deliver it to physical design team again. So this DFT and physical each other throughout the chip designing process. Okay. And again, DFT also interacts with RTL. So each working domain here in one particular project interacts with each other continuously, but majority of the exchange happens between DFT and PD, because PD can start working from DFT because extra logic is added into the existing design what RTL has given. So PD has many stages like floor planning, placement stage, clock tree synthesis, routing stage, final verification. So physical design has many stages, and all this has to be done by a single engineer. But generally, that doesn't happen in reality. Uh, all cannot have the same expertise, but in interview they expect you to answer for everything. Um, that is there, and the work-life balance for physical design is tough. DFT is very good, work-life balance is good. Verification, again, work-life balance is okay. RTL design engineer, work-life balance is very bad. Okay, this is how it is. So once everything is done, it gets into fabrication and then it gets packaged and tested. So this is our basic wafer fabrication process, which we need to know, which we, as a part of semiconductor, we have to understand end of the day how the IC gets manufactured. So we will be aware of all this process, how wafer is getting tested. How wafers are taken, polished, and packaged. So this is a stage it has to go through for a complete chip designing. It has to go through multiple stages, multiples of times. All this will be learned again in the course, part of the course. In clearly, we have 4 to 6 months of time. So these are testers. So testers is something where whatever you have designed so far, okay, a mobile SoC you have designed, but that has to be physically implemented on a silicon wafer, on a chip. It has to become a physical chip. So before becoming a physical chip, you can still test it on a silicon wafer using this tester equipment. So if everything is passing and this tester equipment says that your IC is good, 100% or whatever the expected yield response you wanted, if you get it from this tester, then you go with the mass production. So this is the key point, key place where DFT plays a key role. So to prove that an IC is faulty or not faulty, and this can be okay tested, good to go, can go with multiple shipments or multiple manufacturing. That has to be decided by DFT test patterns. If DFT test patterns are validated successfully, then only anything is possible in a physical world. That's how it is. So there are many type of classes, versions which will work for like mixed signal MCUs, sensors, and RF transceivers. There are A class advanced test company, this particular tester. Similarly, C class for transceiver and RF connectivity MCUs. So there are multiple. So S class is for basically single chip phones, integrated BBSoC, GPU MPUs, massive parallel SoC test L. Okay, at a time you can test uh, multiple SoCs like 3D ICs and all. And scalable A class HVM. This I have worked on this, and S class and L class, all this. Okay. So not everybody will be able to work on lab. The lead and managers, end of the day, the project gets delivered. We need to support the tester team. So there will be separate people, engineers, group of engineers who works in the lab, wearing the lab suit, completely zero dust. Okay, they work in this environment, and we support virtually from laptop. Uh, because we were part of designing, and we are the ones who delivered test patterns, right? So we need to support them while testing. So that is post silicon testing and debug and diagnosis. So likewise, so there are many trends in semiconductors uh, that I wanted to discuss. That we have moved on to silicon, basic silicon. This is the first basic silicon element which we started designing a wafer. From silicon to, we moved on to SiC and gallium nitride. Okay, so which are giving much more power and speed as per the current needs. Okay, we are moving on to high speed networks, faster data transfers, and everything is too much advanced in now, because end of the day the product that is supporting is this element, either it is a silicon or SiC or gallium nitride. If these elements are not there, we cannot design any chip. So a separate engineering happens on this as well, on the base element. So these are the advancements that we have. The gallium nitride is too too high speed, supporting high speed for it is used for data centers. That is working at all the companies that you are seeing now. We are able to utilize our what we call. Let's say that you are able to open any website or any online platform without any delay or latency and you are able to access it at a high speed, high data rates. You are able to download or upload either it may be Instagram, Facebook, or any other in the working environment as well. So the data center has to support it. And if data center, end of the day, data center is again a network chip. It has to be designed with a proper element that should withstand the heat, the speed, everything. So this material, gallium nitride, is one of uh, the best we have now. Okay. Similarly, high powers for wind turbines, railways. Okay, and all the solar power and the industries which work on high power. So silicon carbide is also still working very good. All the latest mobile phones, laptops, the advanced cars with all amenities that you're seeing in today's uh, automobile industry because of these elements. And your fast dash chargers, 120 watts, 65 watts, all this because of this gallium nitride. Okay, so I don't want to go into supply chain disruptions. Now we are going good, but we had this drawback in 2021 and 22. Now 23 has improved a lot. Now 24 is doing very much better in terms of the supply chain disruptions that we had earlier, the geopolitical issues. Okay, now we are doing much better because we have come out of this COVID-19 pandemic. Okay, and multiple wars in last year and before. So end of the day, quality control, yield improvement, and time to market is the final thing. So time to market is a I have witnessed lively for majority of the projects. If you are not in time to the market, you have a competitor somebody, your competitor will come into the market if you don't come in time. So if your project time you are estimated like 1 year, and if you have to finish everything within 6 months, and you have to do marketing for 6 months, then you come to the market. Like how Samsung, Apple does their analysis, and every 6 months they start making that a new model is coming with this features, that features, until release you don't know what exactly the features are going to come. So it's a teasing. So if you don't come in time, somebody else will come, and they will rule the market, and they will just make the money and go. So semiconductor is a money making business, and they there for them the time is so much important, because the highest amount of money that any businessman puts into is in semiconductor in the entire world. So lot of engineers are needed. We lack engineers. Majority of them go into software. Semiconductor, we have less number of people, more openings, less number of people, less awareness into the engineering streams. In colleges, nobody actually teaches or guides the semiconductor. Slowly now things are happening in India, because uh, make in India concept, or fabrication unit started. Macron has started, and its first silicon chip is going to come this month. So everything is on track now, which gives a lot of strength to the upcoming engineers into semiconductor from India. Now it's like a feast. When we started our career, we do not have it. Now it's like a feast that everything is within India itself. Packages are very high in India. More resources are in India. Companies are also growing vastly in hiring. So we need to be ready. That's what I'm talking here. Talent shortage and skills gap. As I said, uh, industry semiconductor companies doesn't train after hiring you. Okay, so even I hire uh, for the last 5 years that I have seen, I hired from multiple institutions when I worked for other companies, and I know what is the gap, the skill gap, how much lacking they are in terms of academic background. They are not learning from training institutes, also properly, not properly training them, and that is what made me start this firm. So awareness is very much important, and this is the best working domain. And for those who have keen into uh, like doing something productivity, like end of the day software, I mean, I don't want to criticize other domains, but if you see any other working domain compared to semiconductor, you are able to design something and bring into market lively, with which you are able to, your that particular IC is your is taking part of your daily life in the form of your smart TV, smart speakers, smart home appliances, your car, okay, your mobile gadgets, laptops, electronic appliances, so everything. So this is more like a uh, fulfilling. Coming from EC background, for me it is more fulfilling, because what I learn and what I'm doing makes much more sense. That's what boosts me uh, in driving every day into this industry. Okay, so we have very high openings in semiconductor. As I said, semiconductor keeps on growing. and there will not be an ending for semiconductor, because semiconductor stops, the technology stops. Technology will never end. So if technology has to grow, it has to speed up. You need semiconductor chip, and if you need semiconductor chip, you need more funding. Companies do more funding. You need more engineers. Okay, so you just need to have a skill to get into it. So get the skill, learn the skill, and get placed. Okay, so any other queries? I'm